Imagine walking up to a massive commercial transport trailer. They're hauling thousands of pounds of perishable food or medicine, maybe even delicate chemicals.
Right, expecting it to be freezing inside.
Exactly. You open the thick insulated door, expecting a blast of Arctic air, but instead, you are hit in the face by a wall of 155-degree heat.
Which is just, it's a complete and catastrophic inversion of the machine's purpose.
It really is. Today, we are looking at a machine whose entire existence is dedicated to creating freezing cold, yet it is actively trying to cook itself to death.
And honestly, it's one of the most fascinating failure states you can encounter in automated engineering.
Okay, let's unpack this because we have a highly unusual stack of sources for this deep dive.
Yeah, we definitely do.
We aren't looking at an investigative journalism piece or, a scientific study. We're looking at a highly technical diagnostic manual for a commercial refrigeration unit.
Right. Specifically, we're going page by page through the protocol for alarm code 9.
Yes, high evaporator temperature. And I want you to look at this document not as a dry, boring maintenance manual, but as a medical chart for a machine in a state of absolute crisis.
That framing is crucial, actually, because complex systems, they don't just break at random.
Right.
They are designed with incredibly intricate intentionality. They monitor their own health, they map out their own potential failures, and they have protocols to forcefully protect themselves when they recognize they are entering dangerous territory.
And this document is essentially a masterclass in deductive reasoning.
Absolutely.
Understanding how engineers map out a machine's failure teaches us how to better troubleshoot complex problems in our own work, or really any system you interact with. So let's start at the crime scene.
Set the stage for us.
Before we can figure out why the machine broke, we have to look at the parameters of the failure. Alarm code 09 is classified in the manual as a shutdown alarm.
Meaning it's serious.
Very. This isn't a check engine light. It doesn't just flash a yellow icon on a dashboard and politely suggest you pull over when you find a convenient exit. It pulls the emergency brake on the entire operation.
It forces a hard stop. The machine is essentially declaring, I am no longer safe to operate under these conditions.
Exactly. And the manual states this shutdown is triggered if the unit is running and hits one of two very specific thresholds.
Okay, what are they?
Either the evaporator coil temperature reaches greater than or equal to 155 degrees Fahrenheit, which, depending on where you're tuning in from, is a scorching 68 degrees Celsius.
Wow, yeah.
Or the discharge air temperature reaches greater than or equal to 135 degrees Fahrenheit or 57 Celsius.
Those are the hard-coded limits of survival for this equipment.
But wait, I have to pause on those numbers. This is a freezer. We are talking about an environment that should be sub-zero. 155 degrees is hot enough to cause severe burns to human skin. It's hot enough to ruin almost any cargo inside. How does a system designed to pump out cold air even possess the physical capability to reach 155 degrees?
What's fascinating here is you're touching on the central paradox of refrigeration physics.
Okay, tell me more.
Well, to create cold, you actually have to move heat. A refrigeration compressor takes a chemical refrigerant gas and squeezes it under immense pressure.
Right.
And that mechanical compression generates a staggering amount of heat. Normally, that scalding hot gas is pumped to a coil outside the box where fans just blow the heat away into the atmosphere.
Makes sense.
Then the cooled, pressurized liquid goes inside, expands, and absorbs the heat from the cargo. But, and this is the key, if that cycle gets corrupted or the heat isn't expelled properly, all of that immense thermal energy gets dumped straight into the insulated box.
So it's actively weaponizing its own mechanical energy against itself. And that explains why the system doesn't just take a break and try again in 10 minutes. The manual states very clearly in bold text, this alarm is cleared manually.
Which is a huge detail.
A human being has to physically go to the control panel, assess the situation, and press a button to allow the machine to turn back on.
Because the machine locks itself out. It cannot trust its own automated recovery protocols anymore. It is actively demanding human intervention.
Now, here is where I get a little hung up on the engineering choices.
Okay.
The manual tells us exactly where this temperature is being read. The sensor responsible for triggering this massive system-wide shutdown is located on something called the evaporator coil suction header plate.
That's a mouthful.
Yeah. First of all, paint a picture for me. Where is that and what is it doing?
Sure. So deep inside the cooling unit, you have the evaporator coils. That's the maze of metal tubes where the refrigerant actually absorbs the heat from the air inside the trailer.
Okay, I can picture that.
The suction header plate is essentially the main collection manifold. It's the junction point where all of those individual tubes merge back together to send the now warm refrigerant gas back to the compressor to get squeezed again.
Okay, so it's the central nervous system junction for the heat transfer. It's the perfect place to take the system's core temperature.
Precisely.
But the manual adds a detail that completely threw me. It says, this specific sensor is an ungraded sensor that does not require calibration.
Oh, yeah.
I have to push back on that design choice. We are talking about a commercial transport unit that probably costs upwards of $50,000, carrying maybe $100,000 of sensitive cargo.
High stakes.
If this single sensor has the power to paralyze the entire operation, shouldn't it be the most precise, finely tuned, highly calibrated piece of technology on the board?
You're falling into the trap of thinking that precision always equals reliability.
It doesn't.
Not in rugged engineering environments. In fact, the opposite is often true. If a sensor requires constant calibration to maintain a tolerance of a fraction of a degree, it means it's fragile.
Oh, I see.
It is prone to drifting out of alignment due to vibration, humidity, or just time. It requires constant maintenance.
So you're saying the engineers intentionally chose a dumber piece of technology?
They chose a more robust piece of technology.
Yeah.
By using an ungraded, calibration-free sensor, the engineers are making a philosophical statement about failure states.
What kind of statement?
They're basically saying, we don't care if the internal temperature is 155.001 degrees or 154.9 degrees. We just need a blunt, unbreakable instrument that screams when things are categorically on fire.
Wow. It's a smoke detector, not a scientific thermometer.
Exactly.
You don't calibrate a smoke detector to tell you what kind of wood is burning. You just need it to make a loud noise so you can get out of the house.
Precisely. The shutdown mechanism has to be as reliable as gravity.
Okay, so the blunt instrument has done its job. It felt the 155-degree heat, slammed on the brakes, and locked the doors. Now, a technician arrives at the scene.
Right.
They are standing in front of a silent, locked-down machine. How do they actually figure out what went wrong? Because you don't just grab a wrench and start blindly loosening bolts on a complex, high-pressure system.
Oh, no. That would be diagnostic malpractice. You'd be destroying the environment of the failure before you even understand it.
Right. You go to the digital tape. The manual dictates that the absolute always first step in the diagnostic procedure is to download the Service Watch data logger.
Essential.
And you do this using a piece of software called the WinTrack Service Tool. It explicitly says the technician must review this data at the technician level to see the conditions present exactly when the alarm was set and when it was cleared.
Yeah.
But what does that actually look like in practice? Is it just a text file that says it got hot at 2:00 p.m.?
Far from it. When a technician plugs their laptop into the unit's microprocessor and boots up WinTrack, they are pulling down a dense, multivariable matrix of telematics.
Like how detailed?
We are talking about millisecond-level snapshots. It shows the ambient outdoor temperature, the engine RPMs, the exact electrical voltage running through the system, the discharge pressure of the compressor,
Wow.
and the open or closed state of every single valve in the system at the exact moment the threshold was crossed.
It reminds me of how crash investigators reconstruct a severe auto accident.
Oh, that's a great comparison.
They don't just look at the crumpled metal wrapped around the tree. They pull the telematics data from the car's internal computer or the black box to see if the driver hit the brakes or the accelerator 3 seconds before impact,
Right.
what the steering angle was, and if the traction control engaged.
That is a much better way to think about it. Historical context is the bedrock of complex diagnostics. Because when a machine fails and shuts down, its resting state is deceptive.
What do you mean by deceptive?
Well, by the time the technician arrives, the pressures have normalized, the localized heat has dissipated, and the moving parts have completely stopped.
Oh, so the machine is hiding the evidence of its own failure just by being turned off.
Exactly.
Yeah.
If you just look at the physical components in their dormant state, everything might appear perfectly functional. The data logger bridges the gap between the aftermath of the event and the precise operational conditions that birthed the event.
It gives you the why before you even look for the what.
Exactly.
So the technician has the WinTrack snapshot. They see the timeline. Now, the manual points them toward the physical hardware.
Right, the usual suspects.
But remarkably, it doesn't tell them to inspect the cooling mechanisms. It points them directly toward the system's heat and defrost operations.
Which brings us back to the physics of why a freezer needs a heater.
Right. Let's walk through the physical breakdown. According to the manual, if the wind track data points to a defrost cycle gone rogue, the technician needs to look at a cascade of physical valves and doors. The first major culprit is the hot gas solenoid. Walk me through how this valve operates, because earlier you mentioned the compressor generates scorching hot gas. How does that factor into a defrost cycle?
Well, when you run a commercial refrigeration cycle, you are constantly pulling moisture out of the air. That humidity inevitably condenses and freezes on the icy evaporator coils.
Naturally.
If you just leave it running continuously, you will eventually build up a massive, solid block of ice that chokes off all airflow.
So it suffocates.
Yeah, the unit will stop cooling entirely, suffocated by its own freezing temperatures.
So the system has to periodically fight its own ice buildup?
It has to actively introduce heat. During a programmed defrost cycle, the system triggers the hot gas solenoid.
And what exactly is that?
A solenoid is just an electromechanical valve, an electromagnet that pulls a plunger to open a pipe. When it opens, it acts as a bypass.
Okay.
Instead of sending that scalding, high-pressure refrigerant gas outside to vent its heat, it reroutes that 200-degree gas directly back into the frozen indoor evaporator coils.
It turns the freezer into a blast furnace for a few minutes to violently melt the ice.
Exactly. And once the ice is gone, the solenoid is supposed to close, and normal cooling resumes. But if that mechanical valve gets stuck in the open position...
Oh, I see. It never stops pumping raw thermal energy into the insulated box?
Right, it becomes a runaway heater.
But the manual also tells the technician to check the defrost damper. It warns that if the damper is stuck in the closed position, it can trigger alarm 9. What is a damper doing in this context?
Think of a damper as a large physical door or a louvered vent within the ductwork.
Okay.
When the hot gas solenoid opens to melt the ice, you don't want all that localized heat blowing out into the main trailer where the frozen food is stored.
Right, you'd ruin the cargo.
So the system actuates the defrost damper, physically closing a door over the coils. It traps the heat in a tiny, confined space right around the frozen metal, maximizing the melting efficiency and protecting the cargo.
Okay, I see the trap. The cycle is supposed to end, the hot gas solenoid is supposed to close, and the damper is supposed to swing back open to let the cold air flow again.
Precisely.
But if the physical hinges on that damper seize up, or the actuator motor burns out, that door stays permanently shut.
And then the unit goes back into its heavy cooling cycle, but the cold air cannot escape the coil housing.
Because it's blocked.
The airflow is completely blocked by a metal door. The compressor is working furiously, generating massive mechanical heat on the back end, but the localized energy has nowhere to go.
Wow.
So the temperature inside that sealed-off section rockets up to 155 degrees.
It's a mechanical failure of containment. The system literally traps its own thermal exhaust and suffocates itself.
Exactly.
And that also perfectly explains the final physical culprit the manual lists, the evaporator fan failing.
Yep.
Even if the valves and doors work perfectly, if the fan motor dies and isn't physically moving the air across the coils to dissipate the energy, the heat just pools in a stagnant pocket until the ungraded sensor screams and shuts the whole operation down.
It's a very logical, physical progression of troubleshooting. You check the pipes, you check the doors, you check the fans, tangible parts breaking in tangible ways.
But here is where it gets really interesting.
Oh, yeah.
Because the diagnostic landscape gets incredibly murky. The manual doesn't stop at physical hardware. It forces the technician to ask a much more paranoid question.
Right.
What if the solenoid is snapping shut perfectly? What if the damper hinges are freshly lubricated and the fan is spinning at full speed? What if the physical anatomy of the machine is flawless, but its brain is completely broken?
Now we are leaving the realm of mechanical failure and entering the incredibly vulnerable world of data integrity.
The manual explicitly warns the technician to look beyond Alarm 9 and check for associated diagnostic codes. Specifically, alarm code 02, which is the evaporator coil sensor, and alarm code 04, the discharge air control sensor.
Central codes.
And it presents two scenarios that show just how fragile automated logic really is. Let's call scenario A the blind timer.
This is one of the most dangerous fallback states a system can enter.
The manual explains that if both the coil temperature sensor and the discharge temperature sensor fail simultaneously, say a wire gets pinched or shorted out, the microprocessor loses its ability to monitor the internal temperature.
It goes completely blind.
It can no longer terminate the defrost cycle based on when the ice is actually melted. Instead, it falls back to a crude backup plan. It terminates on time.
which is a terrible guess.
The manual explicitly warns, if this occurs, the unit may remain in defrost long enough to cause excessive evaporator coil temperature.
The machine is suddenly flying blind, and it has to make a highly destructive guess.
It's exactly like cooking a turkey without a meat thermometer.
Oh, that's a good analogy.
If you don't have a probe telling you the internal temperature is a safe 165 degrees, you just look at a recipe that says cook for 4 hours.
Right.
You blindly leave it in the oven for a set duration based on an average. But if your oven runs a little hot or the turkey is smaller than average, that blind, time-based guess leaves you with a burned, smoking piece of charcoal.
And the refrigeration unit's logic board is doing the exact same calculus.
Wow.
It knows the coils need to be defrosted, but it has lost its eyes. So it says, I'm just going to blast the hot gas bypass for 15 minutes straight because historically that usually melts the ice.
Right.
But because it can't verify the environment, it overshoots the mark, cooks the internal components to 155 degrees, and forces that ungraded shutdown sensor to step in as the absolute last line of defense to save the machine's life.
It's a programmed fallback protocol that actively damages the unit. It chooses the risk of catastrophic overheating over the certainty of freezing solid.
It really does.
Which brings us to scenario B, the true ghost in the machine. We'll call this one the lying sensor.
Ah, yes. This is where we see the ultimate betrayal in automated engineering.
The manual instructs you to check alarm code O2, because if the evaporator coil sensor itself is simply defective, it might just be reading high.
Think about a human fever.
Right. The physical reality of the freezer might be a perfectly safe, chilly 10 degrees. The hot gas valve is closed, the fans are spinning, but the broken sensor is sending a false electrical signal to the microprocessor, claiming it's 155 degrees.
It's a phantom reading.
The heat isn't real, the data is hallucinating, yet this defective reading tricks the system into setting alarm code 09 and pulling the emergency brake on the entire operation anyway.
And this highlights the profound limitation of systems that lack human intuition. The machine is a prisoner of its own electrical inputs.
It reminds me of the Air France Flight 447 tragedy over the Atlantic. The plane was physically fine, the engines were running perfectly, the aerodynamics were sound, but the pitot tubes on the outside of the aircraft froze over and they started feeding wildly incorrect speed data to the flight computers.
Right, a data failure.
The automated system hallucinated an impossible stall and overspeed condition. It trusted the lying sensors over the physical reality of the plane, disengaged the autopilot, and handed a chaotic, blaring, confusing situation back to the human pilots who couldn't decipher what was real and what was a data error.
That is a brilliant and, frankly, terrifying parallel. Automated systems do not possess common sense.
They just don't.
A human technician can put their hand on the metal housing and instantly know, this isn't 155 degrees, it's freezing. The sensor is lying.
Yeah.
But the microprocessor cannot cross-reference reality. It can't say, wait, the hot gas solenoid isn't even open and the compressor's in cooling mode, so it's thermodynamically impossible for it to be 155 degrees right now.
It just blindly obeys the false data. A single lying piece of silicon can trigger a catastrophic systemic shutdown. It forces a massive logistical disruption, potentially spoiling thousands of dollars of sensitive cargo, forcing emergency maintenance calls, rounding a truck all because one tiny component decided to report a fire that didn't exist.
This is exactly why the diagnostic manual forces the technician through this highly specific progression. You cannot just treat the symptom, you have to interrogate the reporting mechanism itself.
And that is exactly why we took this deep dive today. This dry, technical diagnostic manual for a commercial freezer is actually a universal template for critical thinking and problem solving.
If we connect this to the bigger picture,
Yeah,
it applies far beyond mechanical engineering.
absolutely. Whether you are managing a complex corporate team, debugging a million lines of software code, or just trying to fix a bizarre plumbing issue in your basement, the methodology is identical.
Yep.
First, you never rely on the dormant aftermath. You pull the wind track data, you establish the historical context, and look at the exact variables present at the millisecond of the failure.
You reconstruct the crash on the telematics, not the crumpled metal.
Second, you look for the mechanical failures of containment, the stuck solenoids, the closed dampers, the blocked airflow. You look at the tangible reality of the system and see where the physical logic is breaking down.
Right, you check the pipes and the doors.
But finally, and most importantly, you have to elevate your thinking and question the integrity of the data itself. You have to watch out for the blind timer, where failed sensors force a system into destructive guesswork.
Essential.
And you have to watch out for the lying sensor, the false alarm that paralyzes a perfectly healthy system over a phantom threat. You have to ask the paranoid question. Are the systems reporting the problem actually telling the truth?
It really is a masterclass in failure analysis.
But as we wrap up this deep dive, there is one final lingering thought I want you to mull over. It goes all the way back to that strict, bolded rule we mentioned right at the very beginning of the deep dive.
Ah, yes.
The manual states, this alarm is cleared manually.
The absolute demand for a human being.
Right. Think about the incredible, overwhelming sophistication of this refrigeration system. It has service watch data loggers that record environmental telematics down to the millisecond.
It has complex physical arrays of electromechanical solenoids and dampers.
It has multiple redundant layers of sensors constantly talking to a central microprocessor. And yet, when the true crisis hits, when it crosses that 155-degree threshold, this entire automated marvel intentionally paralyzes itself.
Does.
It throws its hands up, locks the doors, and demands a human hand to reset the switch.
It recognizes the limits of its own logic.
But look at the world we are building right now. We are moving rapidly toward a fully automated future.
We really are.
We are designing closed-loop systems, self-driving infrastructure, and AI-managed logistics that are entirely built to fix themselves, to run without any human intervention at all. So what happens to that future when those hyper-advanced machines realize their uncalibrated sensors are lying to them? They hit their own critical thresholds. Wait, scratch that. They hit their own critical thresholds, and there are no human hands left around to manually clear the code.
That is a diagnostic landscape we haven't even begun to map out.
We'll leave you to think about that one.